Hello, welcome to Week 10's class. We start Chapter 6, Entropy. Do you remember the third expression of second law of thermodynamics is to say it is impossible to destroy entropy. So what is entropy? Entropy is a property that we use to describe the direction of a process. We start from the definition. The definition of entropy is derivative, capital S. We use capital S for entropy equal to delta Q over T if the process is reversible. And now we can rewrite this equation. We move temperature to the left-hand side. Derivative capital S, which is entropy. Right-hand side is equal to delta Q. And keeping that in mind, delta Q is just equivalent to derivative Q. The only reason why we don't use derivative before Q is because Q is not a property and a derivative D is reserved for property. But in terms of mathematics, delta Q is just equivalent to derivative Q. Okay, so now we can integrate both left-hand side and right-hand side. So we can tell T times derivative capital S and integral still the same, but we can solve the right-hand side. Integral and then derivative, they cancel each other, so what is left is just Q. You can see we can actually calculate Q from this equation. It looks very similar to the other one, which is W equal to integral P dV. It's very similar. Okay, so our notes, capital S is for entropy. It's a property, and the unit for entropy is joule per Kelvin. And then we use lowercase s usually. What is lowercase s? Lowercase s is just defined as capital S over mass, which we call specific entropy. Therefore, the unit for a specific entropy must be joule per kilogram per Kelvin. Okay, so now next one we introduce is the T versus S diagram. T versus S diagram. Let's recall, we have something very similar. Before today's class, we introduced P versus nu and T versus nu diagram. We're very familiar with T versus nu diagram. We have a vapor dome, and then on this vapor dome, we have constant pressure lines. They curve up, go straight, and then curve up again. You can have multiple of them. So for now, let's sketch two of them, P1 and P2. And according to the rule, P1 must be greater than P2. The higher this line is, the higher the pressure it represents. Okay, and then starting from today, we're gonna use T versus S diagram instead. T versus S, capital S. Usually it's not capital S, usually we use lowercase s. Okay, lowercase s. So now, what does this diagram look like? First of all, you still have vapor dome. You still have vapor dome, and everything is still the same as before. And then you still have constant pressure lines, which still looks the same as before. You curve up, go straight, and curve up. The top one is P1, the bottom one is P2, and P1 will be greater than P2. Same as before. The higher this line is, the higher the pressure it represents. So you can see there's almost no difference. The only difference is we change the x coordinate from specific volume nu to specific entropy lowercase s. Okay, so now next question is, since we know S specific entropy is a property, how do we look for those properties? Next one, retrieving lowercase s. If you're dealing with f point, you look for sf, lowercase sf, or lowercase sg. You can directly go to the tables. And then, just like before, what if you look for specific entropy of a mixture? You can use this weighted average equation. Because it is a mixture, it has two components. They are saturated liquid, point F, and saturated vapor, point G. So now, next question is how much vapor do we have? That's the definition of quality, so multiply by quality. And next, how much liquid do we have? That's the rest, so multiply by 1 minus x. This is the case if you have a mixture, just like before. Okay,